Okay, welcome back. This is part two of the related rates section. We're just going to continue on with two more examples. And let's take a look at this one. So we've got a camera located 3,000 feet from a launching pad of a rocket. And our goal is that we want to point this camera at the rocket continuously after the launch. So the rocket's rising at a given rate of 880 feet per second. As I'm talking here, I'm going to kind of highlight stuff. I saw the word rate, 880 feet per second. That's a rate when we're 4,000 feet off the ground. And then the question is asking how fast is the camera's elevation angle changing? So keywords: fast, how much it's the angle between the camera and the ground changing. Those are things about rates to keep this rocket in sight. Okay, so we've kind of identified there's two quantities, the height of the rocket and then this angle, right? We know one of their rates, we want the other one. Let's draw a picture. I'm not going to try to make this too artistic, but let's say our camera is located right there, and we're told that it's 3,000 feet. So I'll just mark 3,000 along a horizontal here, away from this launch pad that this rocket is rising perpendicularly from. Okay. What's the angle we're talking about? If we draw the hypotenuse of this right triangle, that angle right here, theta, it's the angle of elevation to keep the camera pointed right at the rocket. So you got your rocket up here, you got your camera down here, and the rocket's rising at 880 feet per second. So what's changing? Well, theta of t is changing, so we'll write that down. Theta of t is the angle of elevation. The angle of elevation. What else is changing? The height of the rocket. Let's call it h of t. H of t is the height of the rocket. It's changing in time. Yeah. In fact, we were given its rate of change. We were given, in calculus language, I'll write it, we're given that dh dt is 880 feet per second. Positive because h is increasing as time goes on. 880 feet per second, positive. What do I want? I want d theta dt when h is 4,000. You see that in the paragraph? I want to know what that angle is doing when we're 4,000 feet off the ground. So in terms of our steps, we've got a picture. We've identified what's changing, theta and h. We know what rate we know. We know dh dt. We know what rate we want. So now we need a relationship between theta and h. Theta is an angle in a right triangle. H is the side opposite that angle. The side adjacent to that angle is known. Have you said it already? This is the kind of hard part. It won't always happen super quickly. But one particular relationship is that the tangent of that angle, the tangent of theta, is h over 3,000. Yeah, that's from right triangle trigonometry. The tangent of an angle in a right triangle is the ratio of the side that is opposite that angle to the side length that is adjacent to that angle, right? So that's what we've written down here, h over 3,000. So let's differentiate that. We'll differentiate that equation with respect to t. Derivative of tangent is secant squared times d theta dt, implicit differentiation. That's the quantity I want to know. On the right-hand side here, I've just got, well, 1 over 3,000 is a constant. The derivative of h with respect to t is dh dt. So we can solve that by dividing both sides by secant, multiplying both sides by cosine. I'll put in the units at the end here. I don't really like to write the units during the calculation. So I've got 1 over 3,000 times dh dt. And again, I'm dividing by secant squared, which is the same as multiplying by cosine squared. Okay, so now I'm looking at that thing and I'm wondering, do I have enough information to plug in? 1 over 3,000 is a constant. It's good to go. dh dt, I know, I'm going to replace 880 with it. I need to know this cosine. I need to know the cosine so I can square it. Yeah. So we're going to proceed kind of like what we did in the baseball problem here. When are we looking for this business? We're looking for this business when the rocket is 4,000 feet off the ground, right? So I can kind of redraw the triangle. Sorry, the screen's not very big. I can't keep everything in view at the same time. You have to do a little back and forth. But when that rocket is 4,000 feet off the ground. Technically speaking, it's the Pythagorean theorem, but can you say it with me? If you have a right triangle with side lengths 3,000, 4,000, the legs, then the hypotenuse is going to have length 5,000. It's a scale up of the 3, 4, 5 right triangle. Yeah. So then looking at that triangle, I can tell that the cosine of theta is the adjacent to the hypotenuse ratio. So that's 3/5. So cosine squared is 9/25. So that's what I'm going to substitute in here. So d theta dt is 1 over 3,000 times our 880. And then I'm just going to replace cosine squared with 9 over 25. All right. And if you get out a calculator and you work out that to say 4 decimal places, it's 0.1056. And what would be the units? I suppressed them during the calculation, but what are we measuring theta in? It's an angle, but remember in calculus, when we use these trigonometric functions, we never measure these angles in degrees. It's always in radians. So what that is 0.1056 radians per minute. Okay. Sorry, I've been a little lame about my time units. It's per second. Sorry about that. It's per second. The rocket was rising at 880 feet per second, not feet per minute. So that's in radians per second. Good. Okay. Well, so we can answer the question now. We can say, well, the angle has to change at 0.1056 radians per second. I don't really think in terms of radians in the sense that I have an intuition for it. All right. We have intuition for units that we use all the time. Like I'm an American who lives in California, and if you tell me that it's 54 degrees outside and we're going for a walk, I know I should grab a jacket. But if you told me that it was 14 Celsius, I might have to think, do I need a jacket or not? Because I don't really think in Celsius. I have to do a conversion to know, like, well, how does that feel? What does 14 Celsius feel like? There's a similar phenomenon here for radians. I can work in radians, I know how to convert them, but I don't really have a good intuition for them. So to convert radians to degrees, do you remember how to do that? Maybe I'll just invite you to my office hour. You multiply it by pi over 180. But we could write this. I've done the conversion. I have a calculator sitting here. It's about 6 degrees per second. 6 degrees per second is the equivalent of 0.1056 radians per second. All right, so I have a better intuition for that. 6 degrees per second is what this camera angle has to be changing at. So if we wanted to write our answer, let me look at the question one more time so I know that I'm answering it correctly. It says, how fast must the camera elevation angle change to keep it pointed at the rocket? Well, the camera elevation angle should change. I can't talk and write very well at the same time, at about 6 degrees per second. Okay, there's a nice complete answer to the question. Nice. Okay, one more example. This one's a little bit more elaborate. You can see here that I took this from an old face-to-face calculus class, so we're not going to really have an opportunity to discuss this, but we could if you wanted to come to an office hour, but let's check it out. So it says that we've got some conical filter. We're going to clear some sediment out of a liquid by pouring it through a cone, okay? And that cone is 16 centimeters high. I'm going to draw a picture as we're talking. So I've got this cone, and I'm going to orient it like this in our picture because I'm thinking of it as a filter. Maybe it's a coffee filter. And that cone is 16 centimeters tall. I'm just going to write 16 so the picture doesn't get too busy. It's got a base radius of 4 centimeters. Okay. And then we're going to pour some liquid through it. And this liquid flows out of the cone at a constant rate of 2 cubic centimeters per second. So I'm always searching for information like that. Constant rate, 2 cubic centimeters. And then this discussion question, because there's no related rate question posed yet. So part A, if you look at part A with me, do you think that the depth of the liquid will decrease at a constant rate? So I'm not going to answer that. I'm just going to leave it kind of to you. But the question is, if I rephrase it, so The fluid is flowing out of this cone at a constant rate, 2 cubic centimeters per minute. And what I'm asking you is, would the depth then also be constant? The rate of change of the depth, I mean? Imagine like the fluid level is maybe right here in an intermediate picture. Yeah, so what is the depth I'm talking about? I'm talking about this depth. And the question in part A is, if the volume is changing at a constant rate, decreasing at a constant rate, would the depth as well? You can think about that. All right, I'm going to move on to part B. Part B is kind of the more traditional related rate question. It's saying, well, it wants a formula for the rate of change of the depth. So there's a derivative statement, rate of change of the depth in terms of the depth. And then we're going to use that formula to answer part A. And then part C really is like the previous related rate problems that we've been doing. It's asking, what rate is that depth changing when it's 8 centimeters deep? All right, so I'm trying to consistently use the same color coding in these videos, that I'm highlighting the rates that we know in yellow, and I'm highlighting the rates that we want in blue. So now we need a relationship between the volume of a cone and its depth. Well, the volume of a cone actually depends on more than its depth. The volume of a cone depends on its depth and its radius. So I'm going to start by writing that the volume of a cone, it's always 1/3 the corresponding cylinder. So a cylinder of radius r and height h is pi r squared h, and the volume of a cone is always 1/3 of that. Yeah. So here I should label my variables. V of t is the volume of the fluid. It's changing in time. H of t is the depth of the fluid. R of t is the radius of the fluid cone. And those are all three changing, although we weren't given any information about R and we weren't asked any information about R. So we sort of need to eliminate R. Now, R is going to cause us trouble when we differentiate this equation because we'll have dr dt's in it. So the first thing I'm going to do is try to eliminate R. I'm going to do it with a technique called similar triangles. Let me cut out of this picture so I can see it a little bit better, the two triangles that I'm talking about. One of them is the triangle whose side length is 16 and 4, all right? And the second one is the triangle whose side lengths are H and R. And those triangles are similar in the sense that they all have the same angles. And you recall that ratios of side lengths of similar triangles are in proportion, yeah? The ratios of them are equal. The side lengths are in proportion. So what do I mean by that? I mean, if I looked at the ratio of, say, 16 to 4, the long side of the bigger triangle to the short side of the bigger triangle, that has to give me the same ratio as H over R. Corresponding side lengths of similar triangles are in proportion. Right? So 16 over 4 is equal to H over R. And if we solve that for R, 16 over 4, of course, is 4. So we'd get that H over 4 is R. All right? So I'm going to just put that into my volume formula. I have got an R squared up here. R squared is H squared over 16. So I'll let you kind of check the math here, but if you get all done, plugging in R equals H over 4, what you're going to end up getting is 1/3 of 16, that's 1 over 48 times pi times H cubed. Okay, that's just substituting. Maybe I can help with some color. Substitute H over 4 in for R. You got to square it. So you get H squared times H, that's where the H cube came from. 3 times 16 is 48, and so on. So you can check that out. So here is my relationship between V and H, the two quantities that I have in this problem. So that's what I'm going to be differentiating. So let's do it. We'll differentiate with respect to T. So we get dV dt is equal to pi over 48 as a constant. The derivative of h cubed is 3h squared dh dt, implicitly differentiating. Yeah, what is dV dt? We were given dV dt in that yellow highlighted sentence up there, that the volume is decreasing at a constant rate of 2 cubic centimeters per minute. So dV dt is Did you catch it? -2. It's -2 cubic centimeters per minute because the volume is draining. So if we come over here and put that in this equation, leaving out the units, we have the equation -2 is equal to pi over 16, we'll cancel those 3's, h squared dh dt. And we were asked to solve for the change in the depth in terms of the depth, so I'm just going to solve that equation for dh dt. So what do we have to do that? Well, we have to multiply both sides by 16 over pi and divide by h squared. So we're going to get -32 over pi times h squared. So this is an expression for the rate of change of the depth in terms of the depth, yeah? Rate of change of the depth is over here, and it's in terms of the depth. It's a function of h. Now we can use this to answer part, we can answer part A, right? As time goes on and this depth, is this changing at a constant rate? It's not changing at a constant rate because there's an h in it, yeah? In fact, as h gets smaller and smaller and smaller, this is kind of tying back to our work in the limit chapter, what's this expression going to do as h goes to 0? Right? It's the denominator is going to 0, the numerator is not, it's gonna blow up. So actually, the rate of change of the depth is going to approach negative infinity. Again, the negative sign just means it's draining. So the depth is actually going to be changing faster and faster and faster. And that kind of intuitively makes sense. Imagine this cone when it's full, yeah? And 2 cubic centimeters of water comes out. When it's full, it's not going to change the depth very much at all. But then later on, right, can you imagine, like, if the water line is up here, 2 cubic centimeters comes out, the water line probably you probably can't even notice that. But if the water line was down here, 2 cubic centimeters is going to change it a lot. The depth is going to change quite a bit. Cool, so that's what that confirms. And let's just scroll back up. I got to remind myself of my own question. What is the rate of change of the depth when the depth is 8 centimeters? Okay, well, we are ready to go for that because if the depth is 8 centimeters, then dh dt evaluated at h equals 8. Remember that evaluation bar from a previous lecture? I'm going to use it here again. What do we get? We get -32. 8 squared is 64. So we get -2 over pi. -2 over pi. And do I have a decimal for that? I don't. And sorry, I have an error. My little pause there was my brain trying to, I knew something was wrong here. It's -1 over 2 pi, excuse me. -1 over 2 pi. And what would the units be? Those units would be feet per unit of time. And we were doing this in minutes. So -1 over 2 pi feet per minute. All right, so I hope these examples will help you as you move through your related rate problems in both the activities and the textbooks. I'll say one more time, I know this video is getting a little long, but one more time, these problems are time consuming and you're not supposed to just do them linearly straight through. What you just saw me do in some sense was an illusion because it's a script I practiced and I knew what I was going to do next at every moment. When you're actually solving a related rate problem for the first time, you don't know what to do at every moment, and that's okay. All right, so thanks for listening.